In this video, we'll discuss about energy of a particle executing simple harmonic motion. So let one end of an ideal spring, this is an ideal spring, spring be fastened on a wall, this is the wall, and an object of mass m is attached to the other end. The object is able to move easily on the horizontal and frictionless surface. This is our frictionless surface. Okay. So now by the other by pulling the object, if I pulling this object, the spring is strained slightly, and that due to the elastic property, a restoring force opposite to the applied force is developed. So if I pull the object with the effort, there will be a restoring force F of S to this spring because of the spring property of elastic property of this spring. Okay. And according to Hooke's law, we find out that this restoring force is actually equals to the minus of this displacement. This displacement means when I pull this object from this mean point to this point, another point, this distance is known as displacement. This distance is known as displacement. Okay. So by this I can write this thing as f of s equals to minus of kx. This k is the spring constant. This is the spring constant. So if I see this Hooke's law, I find out that this Hooke's law actually represent our law of simple harmonic motion, the property of a simple harmonic motion. So by this law, or this portion of this this Hooke's law, I find out that this is the property of simple harmonic motion we discussed in our earlier videos. So this is one of the important features of our simple harmonic motion. So I can say that this spring is moving in simple harmonic motion. So suppose the displacement equation of this spring is x equals to a sine omega t plus of del. This is the displacement equation of this spring. Now I know the velocity of our simple harmonic motion is a omega cos of omega t plus of del. Oh, before going to forward, I have to tell you this a represent amplitude. This a represent amplitude. This omega represents angular frequency. And this del represent phase. Okay, x means displacement and this t means time. So this is the equation for our calculating the velocity. So we can also rewrite this thing as like a omega root over of 1 minus sine square omega t plus of del. I rewrite this thing in this format. So I know x is equals to a sine omega t plus del. So what will be the value of sine omega t plus del? It will be equals to x by a. So I can write this thing as a omega root over of 1 minus x by a or not x by, it will be x square by a square. Then I can write this thing as a omega root over of a square minus x square by a square, or I can write this thing as omega root of a square minus x square. So this is the equation for our velocity. Okay, so this is the equation for our calculating velocity. Here one thing I am finding that when our x equals to 0, then our velocity is maximum, which is actually equals to omega a. So this is the maximum velocity to calculating our when calculating the velocity when x is 0, and when x is actually equals to amplitude a, then our v will be minimum, which is equals to 0, because when this x becomes a, then this whole term becomes 0. So this is the two case of our minimum and maximum case of our velocity. Okay, so these two cases are important for solving maths problem. So now coming to the energy part. So we know there is two kind of energy. One is potential energy and another one is kinetic energy. Okay, so what is the formula of potential energy? For spring, because I talk about skins, I know we know that the calculating potential energy, the equation is half of k x square, where k is the spring constant and x is the displacement. And I know the displacement equation is x equals to a sine omega t plus of del. So I can write this thing as a square sine square omega t plus of del. And this spring constant, there is a relation between spring constant and angular frequency, which is actually equals to, we know in our previous video we discussed this, omega square equals to k by m. So I can write this thing as k equals to omega square m. So instead of k, I can write half of omega square and a square sine square omega t plus of del. So this is the equation for our calculating potential energy. Okay, now I have to find out the kinetic energy. I know the for calculating kinetic energy, the equation is half of m v square, half of m v square. So I know the value of v, we discussed in our earlier slide, which is actually equals to, we know there's two equation for v. One equation is v equals to omega a cos of omega t plus del, or I can write this thing as also I can write this thing as omega root over a square minus x square. So I use this formula, then I will get instead of v square we will write omega square a square cos a square omega t plus of del. And if I use this formula, then I can write this thing as half of m omega square into a square minus x square. Okay, so I hope you understand this whole formula, whole equation of this potential energy and kinetic energy. Now I have to find out this total energy. So what will be the equation for our total energy? The formula of total energy is I can write this thing as total energy is actually equals to kinetic energy plus potential energy. So if I use these two formula, then I will get half of m omega square are in common, then I will get, or a square also common, then I will get sine square omega t plus del plus cos square omega t plus del. And I know this equation sine square theta plus cos square theta equals to 1. So this equation must be 1. Then I will only get half of m omega square a square, or I can write this thing as half of k a square, because I know omega square m equals to k. So I can write this thing as half of k a square. This is the total energy of our of a particle executing simple harmonic motion. So let's see this graphical representation of this simple harmonic motion. In this is the x and x prime, and this is the origin O, and this is the y. This origin means the mean position, and this is the displacement minus of n, and this is the displacement plus of n, representing the back and forth displacement, means this one. This represent plus a and this represent minus of a. Now coming back to the our energy equation, we know potential energy equals to half of k x square, or I can write this thing as half of m omega square x square. And for kinetic energy, this equation is half of m omega square a square minus x square. Okay, so if our x equals to 0, then what will be the case? In x equals to 0, our potential energy will be 0. So this is the position for our potential energy when our x equals to 0. But what is the case of kinetic energy? When our x equals to 0, our kinetic energy is equals to half of m omega square a square, or I can write this thing as half of k a square. And this is, we know, this is the total energy of our simple harmonic motion, and this line represent half of k a square, and this line represent 0. Okay, so in this case, when our x equals to 0, our kinetic energy is maximum, whereas our potential energy is minimum. Okay, I hope you understand this point. When our x equals to a, then this equation become half of k square. When our x becomes a, then this equation become half of k square. So this become maximum. So that's why at that point, when x equals to a, this potential energy become maximum, and when x equals to a, our kinetic energy become 0. So this becomes 0. Okay, and when our x equals to minus a, in that case also our potential energy become maximum and our kinetic energy becomes minimum. So from this graphical representation, we find out that always total energy is half of k square, and at when x equals to 0, that means in mean point our kinetic energy is maximum, and in amplitude point, or in the maximum amplitude, our kinetic energy becomes minimum, whereas our potential energy becomes maximum. This is the whole concept of energy of a particle executing simple harmonic motion. I hope you understand this whole concept of simple harmonic motion, or energy of a simple harmonic motion. In our later videos, we'll discuss other topics about simple harmonic motion. Please like this video and do subscribe to our channel. Thank you.